And then just let the transcription pop up so I can close it. So we're gonna pick up where we left off yesterday or Tuesday. Just a quick recap of what we did last class. So we explored basic data types, structures, you know, the variable types. Talked about how functions and libraries work. We get a lot of practice with that through the other sections of this series. We talked a little bit about importing and cleaning data. We really spent a little bit of time on it because it's really hard to teach. It just takes practice. So importing data, the real key there is that there's always a function to read in the data you need. So if you can't find it, you just got to Google harder. Like you're always going to get the only place you'll really run into problems is if data is in a secure format. Like I don't know if R can read from. Oh, does Stata have secure data formats? I didn't know that. Interesting. So I didn't know Stata had security. Yeah, so locked Excel spreadsheets, as far as I know, like the read Excel command has no way to pass a password. That being said, once you're into a locked Excel spreadsheet, you can unlock it. So, yeah, I mean, you could also, you can copy everything to a new spreadsheet and say once you're into a locked Excel spreadsheet, it is no longer locked. Sometimes you gotta, I've done the same thing. Like I've just a balance of I don't want to deal with this. I'd rather just create it and save a new one. So yeah, the locking on Excel spreadsheets is a one-time thing, really. I didn't know Stata had securities, so that's something I'd have to look into. There might be a chance that like read DTA has an argument that could be a password. Just copy it over to, yeah. Again, like once you have it, if you can read it into Stata, you can do whatever you want. So you can just write it out to file, your own file, and then yeah. But these are the kind of things that you run into. Like Microsoft data. What's Microsoft's database product called? Uh, no, they have an actual database program. Doesn't matter. But it stores data in a proprietary format, so it's hard to access from other programs. So like you have to export from that one, but most data formats, and certainly all the statistical data formats, you can access. And we learned about tidyverse and Dippler. So from the tidyverse, the important part was the pipes, right? The X piped into Y, and just understanding the structure of that. It's fairly straightforward. It's actually modeled off of how pipes work in Linux and Unix or anything on a command line. I don't imagine you've had exposure to that, but that's why they do it this way. That's how piping works in operating systems. So the idea that it takes what's on the left side of the pipe and feeds it into the first argument of the next function. And so you get this successive piping. And the reason this works is because so many of the functions particularly in the tidyverse, have a data set as their first argument and have a data set as their output. So they take a data set and they produce a data set. And then that produced data set can be fed into the next function and fed into the next function. And the nice thing is that it lets you write functions sequentially, right? We take X, we apply F to it, and then we take the result of that and we apply G to it. The other option is to just write these nested, where you do F of X, Y, and then you surround that by G. The difference is that the piped version reads sequentially, the nested version reads in to out, and that gets really messy the more complicated, the more you do it. So there's a readability with the tidyverse that is really nice. You'll see a lot of data cleaning becomes a lot easier to follow in the tidyverse. It also, as we'll see today with ggplot, which has the same kind of approach, it lets you build things sequentially, which is really satisfying. So like you can build your variables one by one, or you can build your plot in parts where like you have a simple plot and then you add a smooth line, then you add a legend, and you do it step by step. So it lets you kind of build it in parts and test it as you go. A lot easier than I find Yeah, right. You can do it function by function. So you can do your selecting and your variable manipulation. Then you can do all your mutates at once, and then you can do any kind of pivoting wider to longer. But you do it in parts. That's how you write it, right? You write it that way, and it's helpful to have it built that way. So the three commands we looked at, I think I looked at three with Dippler. Filter is how we filter out rows. Select is how we filter out columns. Mutate is how we create new columns, new variables. Those are the three big ones. Two others that you might run into: rename lets you change the name of a variable. Rename is if you want to change the name of a variable. Mutate is if you just want to make a new variable as a copy of an old one. You don't use rename that often. Rename is most useful when you have bad variable names. One of the nice things about Dippler and the tidyverse is that they don't break column names when you read them in. Sometimes you get Excel spreadsheets where people have designed the spreadsheet in a way that's human readable rather than computer readable. So they've got complex like spaces and really complex variable names. Our tidyverse will just read those all in as a big long string, which is good because it maintains consistency with the spreadsheet, but it makes for really messy code because you have to surround the variables in angle quotes, the top left button on your keyboard, the weird quote up there. So you often use rename if you want to rename those specific variables, the variables that have read in a really messy way. The other one that you might use sometimes is rearrange, arrange. I can't remember. So there are two kind of sorting. You can resort your columns. So that never matters, right? The order of your columns never matters. But when you're working with tibbles in particular, right? When you print a tibble, it gives you like as many columns as it can fit. So it's nice if you can have like whatever columns you need, like your ID column and it's nice to have them at the front. Not important, but you will find yourself doing it just because yeah. The one that is maybe a bit more important is the sort function, which I think is called order, or it might be called arrange, to sort the rows. So again, as far as I know, there are functions there are no, I shouldn't say there are no. Most functions don't care what order your rows are in, but from a presentation or exploration perspective, if you have longitudinal data with multiple observations per subject, you would want them sorted by subject and then by time, just so you can see this is this person's first, second, third, fourth, just for data exploration while you're typing. The two sections we didn't get to that I'm not going to go back to right now, but we might come back to them. I'll explore the too long formatting. If we don't get to it in the third session, we'll get to it in the fourth because we'll need it for mixed effects models for some of the longitudinal data. But switching from long to wide format, as well as joining, so merging data sets. I'll get back to them, like I said, if we run into the need for them. That's all I had for those. So any questions about what we covered before we look at some new stuff? Any questions online? Should pop the chat open just in case. And, oh, I didn't change my our layout. So for today's sessions, I should actually point you to, before we get started, to the GitHub page. So I have today's sessions uploaded as both .rmd and .r files. I'm just working off the .r files because we'll talk about how .rmd files work next session. So if you look in lecture SO2.1 and SO2.2, but if you look in R code, he said confidently, yes, SO2.1 and SO2.2 are those are just the R commands from the two sets of lectures I have prepared for today. So pull those out. That's what we'll be working through. They should be based on all the data that we used last time. A little too big. There we go. It's a little better. So I've changed things up a little bit. So I didn't start with basic plotting. Like R has a built-in a lot of built-in plotting functions, plot, box, hist, that are really useful. And I spent 15 years of my life using that as the primary function. Like both of my theses all the graphics were developed with basic plotting functions. That being said, I think ggplot is nicer. And ggplot is so different from the base functions that I don't think teaching you how the base functions, I think it was worthwhile teaching you how basic data manipulation worked before I showed you Dippler. I don't know that it's worth teaching you how basic data manipulation works before I show you, so it's not worth seeing how the plotting works before I show you ggplot. Ggplot's so different. If you want to see, there's an so2.b, is that what I called it? If you look in the lectures, down at the bottom, there's one called so2.b. That's some background on basic graphics. So how the basic graphic functions work: box plot, histogram. What else did I talk about? Line plots, scatter plots. Those three I explore in detail in here. You might run into those at some point. They're fairly intuitive once you get used to plotting functions. And I would suggest doing, so you might use them for, like I will sometimes, if I'm building a box plot, just use the box plot function because it's a little bit quicker than ggplot. But if I'm preparing anything that I actually want to show people, I'll use ggplot because it's nicer. So these are all the libraries we're going to use. I actually don't know if I use Boomer anymore, but it's an interesting data set, or an interesting library. So the first is just reading my data set and creating my BMI groups, and then making real factors out of sex, diabetes, and hypertension. I'll show you later why that's important. All the functions I think we do today would work if these weren't factorized, but one of the reasons it's good to make sure your factors are properly labeled as factors, and this is true for Stata as well, is that the functions, when they put them into tables and figures, are going to use the levels you have created. So when it builds a box plot and the x-axis is sex, you can either have it as 1, 2, which is how it's stored online, but if you recode it as male-female, it'll be labeled as male-female, and that'll just be easier to read in the future. So I want to talk a bit about what I do here. So here we can see that at the bottom, I've created a reduced data set. So I just want, the Framingham data has 4,400 subjects in it. And just when I'm doing teaching plots, 200 dots is a little just nicer to look at than 4,400. The 4,400 just creates a mess for a lot of particularly the dot plots. So some of the scatter plots I wanted a smaller data set. So set.seed, randomness is not sometimes, is really complicated in computers. It's not as easy a thing as you might think to create a completely random number. What we do is we take a seed number and then perform a complex series of mathematical processes on it to create a random number. But we need that starting number. Famously, one of the security companies online, because the problem is that you would be able to reverse engineer it if you knew that starting seed. It's one of the computer companies online, I should remember them. Their seed is set randomly. They have a video camera pointed at a wall of lava lamps. And they take a picture of it, convert that picture into a number, and that's their seed. So they think it's as random as it could be. Now, I feel like if you were just standing beside it with a camera, they say they do other things as well. It's mostly for show, so they can. This is in their London office. I think they have a big wall of lava lamps by a big glass window. But it's this idea that randomness has a seed for all computer programs, which means that if you set the seed, you get the same randomness. So we should all, when we run this code, we get a random sample of 200 subjects, but we all get the same random sample of 200 subjects. So if you're doing any analysis that involves randomness, so if you're doing any bootstrapping or really most of the machine learning methods, it's good to, before you do like your production version, set the seed at the top of your script and run all your script at once, just so that we all get the same randomness. We all get the same result. We all get the same result over and over, because it's frustrating. Like if you're bootstrapping, you're never going to get the exact same result, but you're going to get the same conclusions. Just your confidence interval might be it might be 2.1 to 3.4, and the next time it's 2.2 to 3.5. Same conclusions, but slightly different numbers. But you want the same number over and over. So setting the seed is what achieves that. So you'll often find in the first, like the top section of a lot of my scripts where I set my libraries and all that stuff, I'll set the seed to 11. 11 is just the number I have defaulted to because it was my high school math. It just sticks in my head. And I'll set the seed at the beginning of a script, even if there's no randomness in the script, like it's just kind of habit and it's just there, it's copied over from previous versions. It doesn't hurt, and it just makes sure that you're going to have consistency in your analysis if there's randomness involved. So we're talking today about ggplot2. That's what the library is called. If you load the tidyverse library, ggplot2 is one of the 8 libraries that loads. It stands for the GG stands for grammar of graphics. So it's a different grammar for plotting than what we're used to. Developed by the same people that developed tidyverse. We'll look at the same graphics as last week. We didn't do that lecture, but we're going to look at line plots, box plots, and histograms. If you look at the R4 Data Science textbook, that online textbook I showed you, chapters 3 and 28 have the most information of ggplot, but the library is used so much throughout the textbook that if you read chapter 3, then when you're reading through the rest of it, you'll just see plots. Because when they're teaching a lot of analytic methods, obviously the first step in analysis is often visualization. So they'll start with that ggplot. So this is what a ggplot command looks like. Ggplot on a data set, and then we add a function. So this is a scatter plot. I created a scatter plot of systolic and diastolic blood pressure. The general structure of a ggplot command is it always starts with ggplot. That's how you tell we're doing some plotting. And then we're adding components to it with this plus operator. Very similar to a pipe, but it's not a pipe, it's a plus. A mistake you will make a lot is trying to build your ggplot functions with pipes instead of plots. And ggplot actually has a very specific error code that says, did you mean to use a plus? So you'll make that mistake. It'll give you an error. You'll change it to a plus. It'll work. It doesn't work, but it's not a big deal to change. So I do it most of the time, I would say, when I'm building my plots, especially if you've been doing a lot of data manipulation beforehand. Is coffee? Oh, yeah. Did you get a plug too?
Yeah.
Okay. You can pull it out.
Oh, is this your? Oh.
No, it's his. I just saw it there, so I'm gonna steal some power while he's not looking. They're more online. I offered it online, so they. Yeah. So the way ggplot works is the primary argument, as with all of the tidyverse, the first argument of ggplot is data, and then it is this. You get a subfunction, which is what you're going to actually plot, and it takes an aesthetic. So every function takes an aesthetic, and the aesthetic is what you're adding. Yeah, like if you look at the arguments the aesthetic takes, I'll scroll back up to the first one. We're going to do a point plot and the aesthetic is X and Y, right? So we're plotting based on X and Y, and we're assigning variables to each of those. There are a lot of different arguments to aesthetics. So the fill, the color, the grouping, all of those can be aesthetics. And you can assign those either constants or variables. And I'll show you more examples of that later. The other thing is, so you can see here, I added the aesthetic at the geome point level. If you add that, you can add aesthetics at the individual function level, or you can add them at the top. If you add them at the top, they get passed down to all the other functions. So it often makes sense to do it more like what this one is right here, where at the basis, I'm building a plot on this data set, and my X and Y axis are defined by these variables. And I do that at the ggplot function because if I have a bunch of different plotting functions, I want them all to use systolic blood pressure as X and diastolic as Y. Someone might have answered it. We'll take a look. Oh, sorry. No, I didn't share the screen. Sorry about that. You should be able to see it now. Yeah, the first 20 minutes of that recording can be pretty boring. Because it's just the camera, so it's just a blank screen. So yeah, so when you pass the aesthetic to ggplot, it passes them down. So if I have geome point just empty, it will inherit the aesthetic from ggplot. And also if I had geome line, because I also want to add a line, it would inherit it from ggplot. So you will often, in the ggplot command, you'll define your X and Y variables, and then maybe also like your group variable if you have groups. It just depends on how you're building your function. The other thing is that because it takes its data set as the first argument, you can pipe into ggplot. So you can see here, the only difference between these two is I'm piping dat reduced in. Seems kind of trivial now, but the nice thing about this is that if I didn't want to do some manipulation on my data set, I can do it before I pass it to ggplot. So let's say I wanted to change, I built a scatter plot, but I want to see it just for people over 55. I could, in this step, between here and here, add a command that says filter age greater than 55, and then pass it to the same plotting function. So it's really useful in terms of separating the data manipulation from the plot, and then you can manipulate the data. Often I'll find one of the things I'm doing here is transforming from wide to long, because the plotting function I'm designing might work better in a long format than a wide. So you can see here's an example of piped my data set in. ggplot, my aesthetic is going to be systolic on the x-axis, diastolic on the y. But then when I build my point, I wanted to add, was it colors for sex? Yeah. An aesthetic where I apply color as sex. One of the funny things about all of the tidyverse, but you'll notice it particularly in ggplot, is because it was developed by a New Zealand team, it supports British English. So you can specify color or colour, O-U-R, if you want. No reason, just defending Commonwealth English, I suppose. But it's nice that you don't get those errors if you spell it the wrong way. I got tricked into spelling color without a U for so long because these are the only functions that do that. Base R doesn't take color with a U, so I got tricked out of it. So you can see here, this is an aesthetic at two different levels where all of the functions below ggplot get systolic and diastolic, but then at drawing the points, I've added specific coloring for sex. So I've added colors for male and female. So if I didn't specify, so that sex just wouldn't be involved at all. It would just be a black and gray plot. So this is what it looks like without the color. Now, you can see here that I can actually pass color as in the top point. I can pass it in the top aesthetic as well. And I would say that most of the time, I specify my aesthetics in the ggplot command because my aesthetics don't tend to change. So I'm specifying them at the top level, and then they propagate down to all the subfunctions. So at the top, I'm going to do a plot on dat reduced. X-axis is systolic, Y-axis is diastolic. I'm going to color things by sex, and I'm going to group them by sex. This is one thing I find out slightly annoying. You'll see more when we go on. And then what we're doing is I'm adding both points, but I'm also going to add a smooth line to it. So if we look here, I get just smooth line estimations of the relationship between systolic and diastolic separately for males and females. You'll see the slightly confusing thing I had to do there was add both a group and a color function. Or sorry, a group and a color aesthetic. So if I just add color, it will color the dots separately, but it won't consider them separately in other functions. If I group them, it will consider them separately, but won't actually group them separately. So you can get some kind of, I mean, if we're being honest, look like mistakes. Oh, sorry, I didn't make this bigger. Oh, Sam, I'm so lazy. So if I run this command, sorry, my libraries are still running. One other thing I'll show you with R is where's the button? I thought there was a pop-out button. Yeah, the zoom button pops the plot out to its own window. If you're working on multiple monitors, which I would suggest if you can, you're going to use that one a lot, right? It's really hard. You're going to get the nice thing about ggplot and the blessing and a curse is how picky you can get about these plots and how much you're going to want to like, oh, maybe I can make this color this way, or oh, I don't like that looks like a gray 55 gradient. I want a gray 35 gradient because I want a slightly less gray. You can do all that, but you often want it big. So almost always when I'm working on these plots, I'll pop this out and put it on my second monitor. And it will still exist down here. So if I run another plot, it will change both the popped out one and the one in my viewer. So you don't have to worry about like not seeing changes you're making. Oh, to keep the old one? Not that I know of. I haven't. There might be something you can scroll with view. I haven't seen in Stata how you can name a graph. Have you done? Yeah, so it makes the Stata graphing go from slightly annoying to actually really useful to be able to run your script and get all your figures side by side. I don't know a way to get those to populate in the viewer as separate tabs. This is somewhere that functional reporting is really useful, which we'll see next lecture, where you can leverage what I have open here, the RMD file, to get your figures side by side. But I don't know a way to do it in RStudio itself. Well, if someone told me it existed, I'd believe them. I just don't know it. Yeah, so if I remove my grouping variable and rerun this, oh, it did work. Sorry, I meant to do it the other way. If I remove my color variable, I think it won't color them. Yeah. So if I remove my color variable, it still gave me estimates for the males and the females, but with no dots to tell it what colors to provide them, it's not that interesting. So it is better off with just with both the colors and the groups. So that you can see, let's say I'm happy with this figure now. Labs is another command where I can change. So if we look at the plot we've created so far, it's not bad, but diab, p, cis BP, and sex in capital letters aren't my favorite. Also, there's no main title, so we can manipulate all of that. There are actually several different arguments you can make to assign. So if you look up online, like how to set a main title or how to set the X label, there are several different ways to do it in ggplot. That argument just gets fed to a bunch of different functions. So you might not use labs, you might use GG title, I can't remember. You'll run into other ones as well. But this one works. So you can see I've added a main title up at the top, changed these to full letters. Also, I took the title off of the legend. You can see I fed it a blank title. And what I did was so this was defined by the color grouping. And what I did was I set the title of the color to blank. Because I don't need it to say that the sexes are male and female. If you know that the lines are male and female, it's kind of implied that it was sex. So I didn't think it needed a title there. You could, if you wanted, put sex here. But yeah, that's how you can manipulate the titles. Right, there are specific functions, like if you just wanted to set the X label, there's a function called XLab, Y labels, YLab, GG title sets just the main title, but one function for all of them. Because usually if you're setting one of them, you want to set all of them, because by default, the X and Y label are just going to be the names of the variables you fed into the function. Like this is DIABP because that's the name of that variable. And you almost never want to go to production with a variable name in your, so you're always going to be setting those. So you might as well set all of them at once. So as you've seen, I've done a fair bit with some line and dot plots. That was the example I went through. There's a couple other arguments that might be interesting. X, Y group color, shape and size are useful as well. If you're comparing them to the base functions, these are the same as PCH and CEX. So you can see that I can set the size and shape manually. I don't know what the scale is for size. Like, I don't know what that is 3 of. I think it's just 3 times bigger than 1, and I don't know what 1 is. So yeah, like it's not pixels, right? It's not, and part of the problem it's difficult is because you'll figure this out if when you go to output these to file, or when a journal asks for like 1200 DPI TIFF images, you'll realize, oh man, I don't know what I'm doing, right? The units here are all relative because we haven't committed to a communication medium yet. So how we, like, if I just export this to a PNG and then export it to a TIFF, I'm going to get different size dots because they interpret things differently. So don't worry about like final file format for now, because you're going to get it wrong. It's going to take kind of a very specific manipulation. R is really good at outputting to PDF, EPS, PNG, JPEG, TIFF, just about all the formats, but they're all slightly different. That's just the nature of really computer science. So I'll talk a bit about that. I don't know if it's in this slide. It might be in that background slide about how you export to, there's some functions to export to file, but they can just be tricky. So yeah, so size and shape. If you want to see the different shapes, so see I assigned shape 17 there. That wasn't by accident. Is it called example? Yeah, yeah. So there's this function called example. If you run example on a function, so there's a plotting function called points. And if I run example on points, it will iterate, it will run all of the code in the examples of the help file for points. So if you look up the points help file, it will give you that example code. This is the only example function I ever run, and it's because of what this third plot looks like. So with plots, it will, if it's non-plotting code, it'll just run all of it. With plots, it will ask you like, here's the next one, here's the next one, here's the next one, this one, the third one. That's what all the numbers mean. So if you want a specific shape, you can probably, if you Google like R point numbers or something like that, I bet you this image comes up. But if you run example on points, the third plot shows you what all of the first 14 are hollow shapes, then filled shapes and a different filled shape, and then some of the characters. I I think the default is 19, and 19 is the one I use the most if it's not the default. One of the reasons I like ggplot as the default is either 19 or 16. In base R, the default is 1, and hollow dots, they just look messier. You can't really see them all that well. I like solid dots more. But yeah, so you can see these aren't, when you're feeding constants in, these are the numbers they take. There's some other interesting plots here, I think. Yeah, yeah, I get it. There we go. So you can see here I've set size to 3, just make the dots bigger, made the shape 17 just to show you what triangles look like. But it's all the same. And but we can actually set size and shape to variables. So in this one, I've made the size equal to the BMI categories, and I've shaped the females differently from the males. Now, I left that color differentiation. I think you really should have both. But you might find yourself doing this to differentiate between your two groups with both shape and color. That's helpful, for example, if these colors probably aren't the best for people who are colorblind. You know, red green colorblind is the most common type of colorblind. Now that's not green green, that's a blue green, and that red is more of a pink red. So I would guess people who are colorblind could tell there's a difference there, but it's not the best contrast as like red and yellow would be. Or red and blue, which used to be the default. So you can see that in the aesthetic, I can either pass constants or I can pass variables. I would say you pass variables probably more often than constants. So the final thing I want to show you is, so I kept I removed the BMI scaling. That's just too much information. If you really need to communicate all that information, you need to find a different way to do it. We'll talk about that in the breakout about some other options. But you can see that size equals false. Oh, I see. Yeah. So I'm going to mess with smooth. So I add the smooth line to it. But, oh yeah, this is what I want to show you is non-aesthetic function arguments. That's what I was getting at here. We mostly talked about arguments of the aesthetic, but every function can also have its own non-aesthetic arguments. So smooth, for example, by default, it adds confidence intervals. And by default, it uses a low S, a running sequential average of the points. I think I linked it somewhere in here, the Wikipedia article for how the low S estimator works, but it's just a running average mostly. But SE, standard error, is the argument for the confidence intervals. So if you set that to false, you don't get those confidence intervals on your line of best fit. And the method as well, if you don't specify it, it defaults to low S, but you can make it LM stands for linear model, so it uses the linear regression model. So you can see that I just added straight line estimates for my two groups. So the functions will take both aesthetic arguments, but also non-aesthetic arguments. So they'll take function-specific arguments as well, and it's a real mix. You'll get used to when you expect an argument to be aesthetic or non-aesthetic, but it's not always obvious. And sometimes I do get a little confused about what is in the aesthetic versus what isn't in the aesthetic. Oh, right. And I also excluded the legend. Just the way it's built, ggplot tends to put a lot of information on the right side, and a lot of it you'll find redundant. So you'll have to learn how to suppress legends. And there's usually like a show legend argument, or there are ways to suppress the legend, because often it's just wasted space over there. So on to box and violin plots. Box plots, I'm sure you've seen a number of box plots. There are a lot of different arguments you can see there. As you can see, most of them are about like how it handles outliers, right? One of the interesting, I say interesting because I don't want to say frustrating, things about box plots is how inconsistent we are as a community about what box plots mean. It's 60-year-old technology. It's been around for generations, and we are not consistent on what the fences mean, right? So how far do you draw the fence? Do you know? Yeah. Well, that's fine, because there's a decent chance you'd be wrong if you guessed it, or you'd be wrong compared to what ggplot does. I don't know if I wrote down what ggplot does. So I believe I know what base R does. So base R draws these lines as 1.5 times the width of the box. So this is the black line's almost always the median. And then these are, I would say the box itself is probably the most consistently defined variable. It's the first and third quartile. So the box is almost always the first and third quartile. The black line's almost always the median. Sometimes it's the mean, but it's almost always the median. And then these lines, I think, are 1.5 times the length of the interquartile range. So it takes this size, multiplies it by 1.5, and puts it on the other side, and then dots outside that. But whether it's 1.5 IQR, whether it's 2 times the standard error, whether it's 3 times the standard error, there's just not a lot of inconsistency. And then dots beyond there. That being said, it's not that important, right? It's getting a sense of skewness. It's a visual inspection before we dig deeper into. Often we're doing this because we want to, we just want to analyze, getting a sense of the data before we dig deep into the mathematics of it. So how the function works itself, you can see that I've set an X aesthetic and a Y aesthetic because I want to stratify. I know I want my BMI groups on the X-axis, and my cholesterol is the variable I want to actually box plot. One of the nice things about this layout, oops, is box plots. Is it? No. So if I plot that, that gives me my box plots. This work? Yes. So it's smart enough to know you want to box plot the categorical variable. So you want to box plot the continuous values stratified by the categories. So if you want horizontal box plots, you can do it. You don't have to trick it. You just tell it, I want the y-axis to be the categorical variable and the x-axis to be the continuous variable. Yes. I don't know what it is, but yes, right? Like it's because yeah, that would be a good point, is like it would make sense on this plot to add like what's the upper limit. What I'm going to show you now is way more useful than anything else I show you, is how to find answers to ggplot. ggplot, add a horizontal line. Yeah, and you know what? We got the two options I want. R4HDS is I was getting their name wrong last time. I think I was saying DHA. They have some of the best intro to this function, this ggplot function websites. So I'll pull them up first. Now, I will say for this kind of question, I would usually hop into Stack Overflow instead. But often if I'm like, how do you draw a histogram in ggplot, which I often Google because there's something with the histogram function that throws me off. Or how do you draw bar plots? Because again, there's something about the bar plot function that I always forget. I don't draw enough bar plots for it to make a difference. So, but here we can see there's a function called geom hline, which makes sense. So, geom hline y-intercept. Okay. So you can see if we wanted to do that, let's get our base plot down. So the other thing to remember is that the functions are actually added sequentially. So it probably makes, so if we put it geom hline y, oops, that was it. You can see what I'm doing there. I'm typing a couple letters, and then I'm not patient enough to wait for it to pop up. If you press Control Space, it'll force it to guess. And as you saw there, my timing was really bad, so it popped up and I removed it. That's a good way to make sure you're getting the function, the variable name, or yeah, the argument name right. So I knew it was I couldn't remember from 10 seconds ago if it was y-int or y-intercept. So we'll add it at 275. Nope, that was okay. The warning keeps popping up, move 52 containing non-finite values. I think what's happening there is that I'm missing 52 cholesterol values. So I'm just getting a warning that if I wanted to suppress that warning, what I could do is I could add a function here, just drop NA on total cholesterol. So that'll reduce my data set. So my data set now has 4382 subjects. It's just, and I believe if I pipe that into here, yeah, now I don't get the warning. So I would never bother to do that just because I don't think about warnings, but certainly you can, it's not a bad thing to do to keep track of your missing values in a reasonable way that way. But ours, because it's only a warning and not an error, I'm not stressed about it. So yeah, so there's and if you look at that STDHA, did I get it wrong again? I got it right that time. There are a whole bunch of arguments. There's line type, there's color, there's size. You can really manipulate that line any way you want. Oh, what I wanted to show, and it didn't work out because grid so is equals 4. So yeah, you can kind of manipulate it as you see fit. Now it is drawing over my box plots, and that's because I've put it, just made a big fat line. um, uh, uh, I had put it after my box plot. If I want it behind those, I just put it on the other side, and now it's kind of hard to tell because I didn't get it down far enough. But when you look closely, you can see that it is behind that line. So there are lots of different. This is one of the reasons that the order of those commands is important because it's going to do them sequentially. So you might mix them up once you're done because you want certain lines ahead or behind or in front of other lines. Oh, that was the other thing I wanted to show you is that the aesthetic I'm using here is fill. So it's giving me black lines with colored input. If I do color, it doesn't give me any fill and makes the outlines a different color. I mean, I think the first one looks better. But just to know that often when you've got big shapes, something that can be filled in, you'll see this with histograms as well. The outlines are the color and the insides of them are fill. And you might set one or both. But if it's coming out and looking weird like this, that's usually what's happening. And I linked to the SCHDA page that really goes deep into what all the arguments are. I tend to prefer violin plots to box plots. They just give you kind of like smooth histograms tilted on their side. They're called density plots, but it just gives you a little bit more information. The other nice thing about violin plots is that they take, as far as I know, almost all the same arguments as box plots. So you can try it with a box plot and then switch it to a violin to see if you like the violin more. And sometimes you will, sometimes you won't, but it's just nice to have another option. Because violin plots, especially if your concern is around skewness, violin plots are a really useful way to investigate skewness. So yeah, you can see that we have a little bit of cholesterol skewness in these two groups. And probably some errors in this data. I don't think a cholesterol of 600 makes sense. I don't know anything about cholesterol, but I don't think it makes sense. So on to bar plots and histograms. Start with histogram. Yeah, start with histograms. They use the geom histogram command. The big difference here is we only have one aesthetic, right? The histogram really only has one axis. You only set one axis, right? I want to do a histogram of cholesterol. And then the y-axis is going to be counts or frequencies, right? It's the density. So when you look at the aesthetic, we only have one aesthetic. if we add another aesthetic, stratifying it, we get the stratified version here. Where the default option is to stack them, which I don't find that useful. Sometimes it is, but in general, I don't know if it's adding a ton to the process. So if we can also make them overlap, which here is kind of not great because I can't see the other one, right? The overlapping of solid colors. There's an argument called alpha. Oh, did I not set it? I didn't include it. Too far. So this is what my I remember I'm gonna have to look up to oh, maybe the SDHDA provides some insight into it. Can't remember exactly how to set the alpha, but the alpha channel in a color controls the transparency of it. So if you want to overlap histograms, you're going to need to add some transparency so you can see through it. And I can't remember exactly how that works. Oh, it's just an argument. Yeah, so if you have an alpha channel, uh, that's that looks okay on that TV. Another challenging thing about working with the graphics is how different they're going to look on different screens and projectors and colors. But yeah, so there's an alpha argument that can set the transparency of a histogram. But histograms are pretty straightforward depending on what you're trying to build. Oh, did I not? Yeah, I did. So here you can see the same thing that if I do a bar plot. Now for a bar plot, I'm going to be doing it on BMI groups as my X value. I'm going to be grouping and coloring it by getting different bar plots for males and females. Again, the default is stacked. I don't love this look of stacked bar plots. So if I change my position to dodge, and that looks a lot better, the idea of putting one on the left, the other on the right. And not surprisingly, I linked to the third SDHDA. Like I said, SDHDA really, really useful for learning the basics. And by the basics, I mean everything of how to, of the kind of the basic, like the geom underscore something for all the plotting, line, hist, smooth, box, violin. There must be some others, but yeah, so it's really useful for those kind of learning both the basics and it's one of those, it just keeps going, and by the end of it, it has almost definitely explored everything you might want to do. So it's a really useful website. So I'm going to give you some time. Doing well. I think I'd scheduled 90 minutes for this session. Why don't we take 25 minutes, 5 minutes per plot. I'll come back. I'll check in with you every 5 or 10 minutes to see how you're doing with these five. So a scatter plot of cholesterol versus BMI, histogram of systolic blood pressure, violin plot of systolic blood pressure stratified by sex. So why don't we take 10 minutes on those first three, and then the last two take a little more work, including some searching. So we'll take 10 minutes. People online, you guys can talk amongst yourselves, and we'll come back in 10 minutes to talk about those first three, and then we'll do 4 and 5 after. Where's my water? All right, I'll be right back. I gotta find my water. I should leave that up. Makes more sense. Press. To do. That's good. So how far has everyone made it? Did you get the first one done? The violin plot? A couple minutes. And then we'll go over those first three. All right, let's start with these first three. So for the scatter plot, what did you want to give me a hint of what you typed? People online can chime in as well. Oh yeah, yeah. So that's kind of the base one. I would add an x equals here. What you did was fine. It so often there are a lot of functions you'll see where the you can enter the function arguments without specifying what you're feeding it to, because it just expects the first one is x, second one's y. Um, it's probably good practice to specify those as much as possible. That being said, the way you'd written is fine. So this would work. Whoops. That would work. I didn't actually feed the data set. My bad. Um, I was doing this weird pop-out thing. Yeah, looks fine. Yes, that's a fine setup. And yeah, you can add colors for sec, grouping for sex. So there are a lot of different you can make. But in terms of actual scatter plot of cholesterol versus BMI, that's fine. And also, like, you picked X and Y probably because that's the way I wrote them. But there's no reason you couldn't do it the other way. There's no real we don't have a response and a predictor here. There's no dependent and independent variable. We're just plotting. We're just looking at a correlation. then for the histogram, what did it look like? I got the rest of it off myself. Anyone online want to chime in? Eric or Tassin? So what did you have for your aesthetic here? Oh yeah. New color. So then your hist command was empty, or do you have something in there too? Oh, you have them in, you have them there. Okay. Like that. I do that so much. The command in baseR is hist, not histogram. Oh, so here you can see what happens if you set color instead of fill. That looks bad. That's, I don't know what you want to do, but you don't want to do that. Yeah, I just typed it wrong when I wasn't. So that looks okay. And then if we wanted to do, we had alpha equals 0.5, we'll make it see-through. And the other one was, is it position equals dodge? Oh, that's no good. So we don't want position. Um, This is actually a good example of working with ggplot will teach you to just in general be good about where you write, save, and recall your code, because you'll create plots that you're proud of, that you like, and you'll want to go back to them. For the exact example that we're doing right now, I want those overlapping histograms, and I know what I want to do. I just can't remember what the command is. So if I go back to actually this tutorial, um, position equals identity. That's what it is. There's some there's some arguments in, I mean, all programming languages have this problem. There's some arguments that just don't make a ton of sense. Like they're just really not intuitive. And I find that position equals identity is one of them. Like I always have to look it up because I'm not going to remember what that means. But you don't have to do it that way. It works without these last two arguments. That just gives you a stacked bar plot. But because these bar plots are, because these histograms overlap so completely, um, it's not the most interesting kind of use of the alpha channel either, because it looks like one's just kind of enveloping the other. When we do the third one. Yeah, go ahead. Oh yeah, right. So this is what it looks like without the quartiles, just as basic violin plots. That's often fine. These aren't, I don't publish box plots very often. Journal space is very precious, and it's just exploratory, right? You're not going to communicate. It's for you to understand your data before you get into it. But if you wanted to, I'm just going to copy what I had from here. Draw quantiles. That's the command I forgot. Yeah, so there we go. If we just want to get the quantiles in. Do that now. Yes, that's pretty good to get the hang of it. The last two are a little bit more work. So we just want to do that. We want to take the same audience systolic versus but you could do cholesterol and BMI, but reduce it just for people with normal BMI. That's not a ggplot command. And then the second one, we didn't talk about how to do it, but there are two commands called facet by BMI K, or facet wrap would be the most effective command. So try figuring out that second one. And typically, uh, with these ones, when you want to do stratified plots, it's to build one big plot, and then you stratify them with that facet wrap command. So take a look at that, and we'll, I'll just give you 5 more minutes, and then we'll come back to that one. Dippler command. So Dippler is what we talked about at the end of last class. Those are the data manipulation techniques. So in this example, if you want to do a ggplot on a restricted data set, it's easier to restrict the data that's being fed in than it is to restrict it within ggplot. There probably is a way to restrict it within ggplot, but the easiest way is, rather than passing a full data set, pass a reduced data set. So you do the reduction, you do the data reduction before it gets to ggplot, and that's one of the tricks when you're doing a lot of this plotting is the ggplot process will often be smoother if you can manage to do the data manipulation first. I should probably grab my plug again. I need to grab my plug. I forgot that. Especially like the webcasting and everything. 3 hours, just a lot to ask my battery, I think. Yep. It requires a function call. Yeah, so you're on the right track. Let's see what you got written there. Yeah, but you need to, the right side of the pipe operator needs to go to a function. So you need to pass that into a function that will reduce it to only to BMI equals normal. So you're on the right track, but we need one of those named functions like filter select or mutate. And if we're subsetting rows, subsetting subjects, filter would make the most sense. Go back to your R console for a second. Yeah, you're pretty close. I just wanted to see what your backtrace. I've never used last trace before. Oh, does it work? I'll run our last trace to see where the error occurred. Cool. That's really useful. I mean, it looks like a mess.
Yeah, sure. Once I start talking.
Yeah, so you can see what it's
Things like reading this is not but like I copy pasted this.
stop X must. It's actually the problem is the Framingham first data set. So what is your so what it's saying is that X must be numeric, which means it's not reading BMI as numeric.
I think it might be I don't have it kind of like clean and done nicely. I think I just imported a new data set and tried to run it.
Yeah, so BMI is a character. So it's what you could do actually. So if you just make a blank line above BMI groups, yeah, within the mutate command, and just type BMI equals as dot numeric. And then put BMI again. So that's just converting BMI to a number. Yeah, it's fine. You've got an extra set of brackets there, but they're not going to break anything. You're missing, so one mistake everyone always makes, you're missing a comma at the end of that line. So you just need a comma right there. Yeah. One warning in mutate. That's really useful. Yeah. Yeah, and that's what we expected. So the NAs by coercion means that it converted all of the. Yeah, so I think that data set has missings as dots, so that's why that read it as a character. So yeah, so your data set should be correctly BMI now. So that filter command is right. You've got that set up right, but the thing is that you're not feeding this to anything.
So does this have to live like underneath here?
Yeah.
Okay.
Yeah, so you can do it that way. Yeah, so you can put that there, and you would want to delete the dot reduced because you're piping it in. Yeah, that looks right. So yeah, for that first one, I'll give you a second on the second one because you do have to learn a new function. But for that first one, as I said before, when you're trying to subset data, the easiest way to like subset a plot is in the data set. So if we want to reduce it to just a normal BMI group, we add a filter that is BMI groups equals normal. And then don't forget your second pipe. I guess I really have no idea if that's right, because it's the other thing you'll see in this plot that I find looks really bad once you notice it is integer spacing, right? Because we call them systolic and diastolic, but even though I could have a systolic of 118.4, in reality, no one gets that. Everyone gets whole number. So you get this gridding pattern. You'll see this often in ages as well, because your age is never recorded as 40.3. It's always just a whole number. You're your integer until your next integer. So because of that, you get this gridding effect, which once you see it, now there is a way around that, and this isn't just an aesthetic thing. This can actually be useful sometimes. There's a function called and it didn't do very much, but you can kind of see that it's added a little bit of variance. You can control how much variation it adds, but if you're getting a lot of collision in your dots, like you've got a dot and you know that it probably represents like 25 or 30 people, adding a jitter to it to kind of spread them out can sometimes make it a little bit more readable. And jitter is very much one that I would use for my own data exploration, but I would almost never publish a figure with jitters in it unless I had a really good reason for it, just because it doesn't actually represent the data, and you just don't tend to have space for it. So the final one, rather than just normal, I want the 4 BMI categories in a single figure. And the hint I gave on the other slide is that there's a function called facet wrap. Yes, that looks right. Yeah. Oh, I didn't know that's how it worked. Vars. Huh. I've always seen it with a function. Yeah, let me see where you got it. Okay.
Because I keep accidentally just like.
In the editor, a Control Z will do it.
Oh, I do the same thing with static. I'll do like Command Shift D to like run it.
Yeah, Control Z will undo, and there's a redo as well, but I think it's in the edit drop down. I don't actually know what the redo is. Oh, interesting. It changed. These all are. It takes form, right? Facets. For the variable. For compatibility with the classic interface, man. R just makes me feel old all the time. Yeah, yeah. And it lets you like if you wanted to create a new variable for coloring, you could create it just here. And you don't, one of the nice things about this approach is it lets you create these kind of plot specific data sets that you don't need to save in your workspace. But let's say I did do some manipulation here and I wanted to save it, it would be really easy for me to like D equals and then D like that. So like if you were creating a data set before ggplot and you need the data manipulation you're doing before plotting is something you need to save long term, so you don't need to create that data set. Yeah, so you'll find one thing you might find is that you might just, depending how complicated it gets, you might take like whole code chunks, and like you might have a separate R scripts for your sensitivity analyses, where the very end of your data processing step is subsetting the data set, and then you can just run your same analysis each time. And hopefully it'll work the same. Sometimes you never know what's going to break when you subset a data set. Like there might be places where we're stratifying that don't stratify anymore. So you never know what'll happen when you subset the data. Sometimes it'll break, but usually it won't. As Laura, right? As Laura corrected my old ass, that the way you're actually supposed to do this is like this. Is that right? Yeah. The way that I had learned it was like this one out. Yes. So yeah, so there's an export button there. The other option you can do is the commands to save things. So they're actual code commands, and it looks. Where's that? I didn't port it over from the background. So if you look at that background file I'd mentioned, down at the bottom of it is how to save images. So you can. Where's my here? So the command I tend to use the most is PDF, so2.1.pdf, height equals 7, width equals 7. So this PDF command, it basically opens a PDF file, and then all the graphics you produce get written to that PDF file. And then once you're done writing to it, you add a command called dev.off, and that turns off the writer to the PDF file and saves it. So you can do a bunch of different plots. Yeah, it can be really useful if you're trying to produce a bunch of graphs at once. One I did for Jill's meta-analysis that writes forest plots is that much text on a visualization gets messed. But actually, I have another one. I wonder if I can find it. Where the point of the research, we were looking at quality of life trajectories in individuals, and there were 200 people or something, and the numbers were all coming out wonky, and I was trying to figure out what was causing it. So we produced individual quality graphs for all 152 people and exported it all to a PDF. So then you could quickly scroll through the PDF. I would, as a default, make PDF your export file format of choice, because the vector-based graphics are just going to be way crisper than ours supports real vector-based graphics. So what that means that, look how I run this and show you. So that should here. So that's the one we just saved to, I should have made the two figures. So the height, and we're talking about, we don't know what units these are. For the PDF, I think the default unit is inches. So I want, I'll make it 11. There we go. Um, if you're on Windows, I'd recommend the Sumatra PDF reader for one really nerdy reason, in that if you have a PDF file open, a program can write to that PDF and overwrite it, and the PDF will update. It comes up almost never, but it's super annoying when you're stuck in the other. I think the default Mac PDF, the preview, will do the same thing. But I found this really helpful. This it, update the PDF, reopen it like I would with Adobe. Sumatra PDF, Sumatra PDF. It's also the other reason I like it is, as you can see, it's got tabbed browsing at the top, and it's just super lightweight. I find it just opens quicker than the Adobe be on your computer anyway, because there's certain technology doesn't work with it. Where with Sumatra, but Sumatra just lightweight. So I'm still getting images because vector graphics don't, like a PNG or a JPEG or even I think even a TIFF is ultimately a matrix, right? It gives you a matrix and says in this square draw this color. The way they get away with PNGs looking crisp is the grid is, a billion points, but it's still ultimately you can get pixelation. A PDF doesn't say fill in this color, it says draw a dot at this point. So it's specifying them all based on points. So regardless of how far you come in, with PDF-based figures is that because it's drawing each point individually, if your data set is 10,000 points, it's good. You'll feel it when you load it. And if especially if it's a 10,000 point scatter plot and you exported 5 scatter plots to your PDF, it is drawing 50,000 points, and you might see it like chunk as it loads. But computers are getting faster every year, so if what was a problem during my thesis might not be as big a problem anymore. But so I use PDF because it's the crispest, but don't try and convince journals that. They will ask for, there's a very similar command for PNG, for TIFF, for EPS, for JPEG. All of the place you get caught is, so for PDF, the default height and weight, I think are height and width are centimeters. For PNG, I think the default is pixels. So you'd want to change it to like 600 by 800, like a different kind of scale. As well, you'll get some journals that will be requesting certain DPIs, dots per inch. That isn't an argument in R that I know of. So one of those things you Google, like R TIFF 1200 DPI, and someone will give you the algebra of it, right? Like you need this many PNGs and this. There's like a resolution variable. You'll be annoyed with it. You'll fiddle with it about. Does it give me the? Yeah, so you can manipulate certain parts. The reason I would avoid using the export button is that it's not repeatable, right? So like the nice thing about writing it to file is that when you inevitably get told that like they will get rewritten, yeah. But like if you create a figure and submit it to something and get told like the file format's wrong, it's nice to be able to change your script and adjust it rather than trying to figure out what you did the last time. Yeah, that's actually the biggest, is exported it right. Like you figured out the stupid settings to get the journal to accept it. But then they decide the extra $1,200 for color, can you switch this to grayscale? Stata is pretty good about that. Yeah, Stata has a lot of drop-down menus. And R is kind of learned from Stata and SAS that way, and that R has some, was it you or someone else last time that did the data import using the import command? And R, if you use the R point and click imports, it prints out the command it ran. Stata's good about that as well. So I don't see that. I don't think that was coming up for the, no, it's not printing out the commands it's using for the exporter. Might be because it's not, those drop click and clicks, like every time the report, you understand less and less. Like the Mac and the Windows one are different because the like, so PNGs are weird. They're the best trade-off of quality and file size. They're so small. They scale well from really tiny, like icons are always PNG. The tough thing with PNGs is that they're good at the size you have them. They don't zoom in well. So that's one of the challenges, that like you prepare a PNG for your journal, it looks good in that column, but then you go to bring it into your thesis and you stretch it twice as big and it looks real bad. So PNGs are great at the size they're at. I mean, all of these are PNGs, right? Like they look good there, but it doesn't take of zooming in. That's not bad, I guess. These must be pretty high quality. I've never actually checked to see what it. The other nice thing about PNGs is that they can embed as text. So if you look at I think I did embedded text here. If you look at this HTML file, it's an entirely text-based. It's like it's all one file. Like if you look at the source for this image, it's just file equals and then a huge line of hex code. So it's really nice that like this HTML file is encapsulated, is the word they use. It's all one file. So I can email this HTML file to someone as a single, can open it rather than having to like, yeah. File. Sure. Any questions? That's fine. If not, we're going to actually learn some stats. So we've got an hour and a bit. Let's learn biostats 1. You guys are all experts at this, so we'll get through it pretty quickly. So one thing I've included the read command 2 different times, 2 different ways. So the top one uses base read.csv. It's got some arguments and creates all the variables. The second one is the tidyverse version. Even you can see I used read_CSV. So Dippler has its own CSV reader that just reads a tibble rather than a data frame. They're very similar, but their arguments are all different. So both of these work. There's not a right or wrong way to do it. I would say that more often now I use this second one, but I would never replace the first one if it already exists, because the result of either the first command or the second command produces the data set. So what I'm hoping to get over is hypothesis testing, so t-test, chi-square test, Fisher tests, and then our regression methods. Linear, logistic, maybe we'll get the Poisson. Once you learn in terms of methods. I don't know if I've talked a lot about formulas yet. I know it's come up. Well, I thought it would come up in FacetWrap, but they've changed how that works. So the basic idea of a formula in R is, so in Stata, when you want to do y equals and then a series of x's, it's just the variable separated by spaces, right? And it's assumed that the first variable is your dependent variable, your y, and then everything after is your x. And if you want to do an interaction between things, it's a star, is it a colon? star. That's one of those things that I would try and it would break, and then I Google it and I get it right. In R, we put the things on the left, or sorry for you guys, the left's over here. Put things on the left is Y, and then a tilde, everything after the tilde are the X's, are the independent variables. And rather than separated by spaces, they're separated by pluses. So if I want to predict systolic blood pressure with sex and diabetes, I do systolic tilde sex plus diabetes. And then if I want, yeah, it's you get the hang of it pretty quickly. If I wanted to do an interaction between sex and diabetes, I would just have a times, a star. So order matters as much as if order matters, it will make a difference. So you can see here, this is the box plot. So this is the base box plot function, not the ggplot one. This is a box plot of systolic blood pressure stratified by sex and diabetes. And this one is see that we got these two represent non-diabetics, male and female. And then if we go down to the males, non-diabetes, diabetes. So you can see that there's just a difference, like the order matters. It doesn't matter very often, right? There are very few situations. I want to say none, but someone would correct me if I said none, where like, if you're doing a regression, the order of the variables doesn't normally matter, but it does process them in an order. So if you wanted like the controlling variables at the top and then your actual effect variables at the bottom, you would just order them that way, or vice versa, however you want to organize it. So on to the t-tests, the command is t.test. And there are several different ways to do it depending on the type of t-test you're doing. So if you pass it a single vector like X there, it does a one sample t-test. The default null hypothesis mu is 0, so it t-tested against 0. You can set this if you had a value. I mean, we teach one sample hypothesis tests, we never do them, so it's not a huge concern. If you want to compare two vectors, X and Y, you would just do t-test X comma Y. That compares the values in X to the values in Y. If they're paired, so if it's like a before and after thing, you could do paired equals true. You could also create a new variable that's a difference between Y and X and do a one sample t-test on that new variable Z if you wanted to. And then finally, if you want to stratify a variable by another, that's where you'd use your tilde. And that's probably actually the most likely way you're going to do it, because that's how your data is organized, right? Your data is not going to have a column of male blood pressures and a column of female blood pressures. It's going to have blood pressure, sex. So if we want to test blood pressure between men and women, we would do systolic blood pressure tilde sex, and that would stratify it for us. So when we run the command, we get output that looks like that road. If we run the t-test itself, if we run it without assigning it to an object, it gives us the default print value. That's true for all the functions. So if you run a function, don't assign it to an object, it just gives you the output. But you're usually going to want to assign it to an object because you want to be able to pull up the specific values. If we test on systolic blood pressure, this is testing against mu of 0. That doesn't make any sense. Of course, our p-value is super significant, but it's systolic blood pressure being greater than 0 doesn't mean anything. But it gives us our confidence interval and the average. And really, these are the numbers we care about more. The p-value is not that important. What's far more important is that average and that confidence interval. So we want to learn how to extract that. You can see in the next line, if we change the mu value, so now we're testing it against a systolic of 130, we get, we still get a gigantic p-value. The test statistic did shrink significantly, but 8 is still a giant test statistic in the grand scheme of things. But the average and the confidence interval obviously didn't change because the confidence interval on a t-test isn't dependent on your null hypothesis. It's the confidence around that average. So what we're normally going to do is assign our t-test to an object. Then you can either just print the object just by typing it, but you can also extract elements. And this is where I said part of the this. So I've created a t-test 01 object. There are a bunch of different ways we can learn what in that object. So we can type it like this. This gives me that same print output. Names gives me the, this is all the attributes it has. Now, I don't normally use this thing, but if you look at the tab, do you guys see the environment tab? This is a list of everything that is in your workspace right now. And if you click on any object, it will pop up like a description of what is in it. This is really useful when you're first learning what these objects, like when you're first learning these objects, to figure out what's in there and what you can extract, because this is a list of everything I can extract from the object. So you can see that you're better off looking, I'll point at things, but this is a slide I can't make the fonts bigger on, so you're kind of stuck with unreadable information. But you can see the first object, the first object in t-test 01 is an object called statistic. And if you read over to the right, we actually know it's 8.63, whatever. So that's the test statistic. The second object is the parameter. That must be the degrees of freedom. Third is the p-value. Fourth is the confidence interval. We can see it's a double of length 2. So it's a 2-length vector. It's the low and the high estimate. The estimate, the null value, and all those other elements. So if we but the estimate and confidence interval are the ones that are probably the most important to us, right? That average, and then the confidence interval is the lower and higher value. And we can pull those actual numbers out to later put into a table for production. We'll talk about that more next session when we talk about functional reporting. Because functional reporting is where we'll learn how to like run a bunch of t-tests and pull things out of each individual t-test for purposes. So if you pass it 2 vectors, obviously it does a test comparing the 2 vectors. Although again, no one would ever do a t-test comparing systolic to diastolic blood pressure. That's just not an interesting number. You might compare 2 values in order to get these numbers, right? The means of each group and the confidence interval on their difference. So if you wanted those numbers, you could get a t-test. You can see got the test comparing systolic blood pressure stratified by sex. So cis-BP tilde sex. I've referenced it with $signs there, but almost all functions will take a data set as an argument. And if they do, you don't need the $sign. So you could either do dat $cis-BP tilde dat $sex, or cis-BP tilde sex data equals dat. Passing in a data set, it's useful. You have to type dat $sign less. You're going to need it when you do linear regressions, because if you have like 8 predictors in your regression model, you don't want to type dat $sign 9 times. So it's a lot easier to pass in a data set. Here, another option is if you really wanted to use the non-formula version, you could pull out the male and the female blood pressures into 2 different vectors and then test those vectors. And the only reason I showed you this is I want to show you the t-apply function. So I think I'd mentioned before, but functions are really useful ways to do something across a bunch of things. So apply, for example, is a great way to run a function across either each column or each row. So apply lets you, if you want to do something on every column in a data set, apply would be helpful, or every row in a data set. Sapply is a function that's good for doing something to every element of a list or every element of a data frame. Tapply is probably the one I use the most. Basically, it takes a vector of values x and an index vector index. What it does is it takes those values of X, breaks them up according to the groups in index, and then does really whatever we want. So we can pass it a function, and it'll apply that function to the values of X stratified by the levels of index. So if I take systolic blood pressure, stratify it by sex, and get the mean, that gives me the mean for males and females. Likewise, if I, instead of sex, my groups, it gives me. I will say that when you use tapply with plotting, the titles are a mess and I don't know how to fix them. So it's not something we do a lot. What we did here was here. I took my systolic blood pressures and the index is sex, and the function I passed was concatenate. So it just gives me a list where the first element is all the female first or is male first? I can't remember. Interesting. That almost always means that we broke our systolic blood pressure variable somehow. So the first thing you'll want to do when you start getting an error on a variable like that is just print the variable to the, so like go to the bottom. Let me see what your last error was. Just oh, weird. Okay.
It was sex, actually. Grouping factors at exactly 2 levels.
Yeah, so something's wrong with your sex variable, and my guess is that it might be empty. So often, yeah, it's half. So
Oh yeah, it is empty. There you go. How did that happen?
so if we go back to our data processing, my guess is it has to do with how I wrote it. So if you look here, so yeah. So the problem is that if you don't rerun this, so like if we
Like,
run,
together.
yeah, so if we go like, just run a couple lines. So if we just do all this, sex should work, right? If we go to 2 dat $sign, it looks right. The problem is if we try and run this command now, what it's going to do is it's going to take sex, try and make it a factor, and tell it has levels 1 and 2. And it doesn't have any of those things, right? None of those are true. So if we run this command, nothing breaks because we get no errors. But if we were to look at, now it's missing because the levels weren't 1 and 2, they were male and female. So I would guess that that's what happened.
That like homework. I'll check it out. You like clearing the data in memory. I mean, clear kind of equivalent way to do that now.
Yeah, so yeah, so if you want to clear memory, there are 2 ways to do it. Just the RM open bracket, close bracket will clear the workspace. It'll leave your libraries loaded. Also, if you go up to session, restart R, that takes you back to basics. That's as if you closed and reopened the program. I tend to do that a lot. The difference between the two is that if you restart R, you have to reload your libraries. But if I'm worried that I've messed something up, there's just as good a chance I messed it up at the library level as the code level. So I often, and the fact that I have that, it's Control-Shift-F10 is the command to do it. The fact that I have that memorized shows how often I do it. Yeah, it's one of those things that like you've been working for a while, you got the thing you're working on finished, and you're just not sure. It's like, did I do everything in the right order? Because I've been working on this for 45 minutes. Restart R and run it down to there. One of the nice things next class, we can all the code above where I am. So like if your code is, so you got 1,000 lines and you're futzing around in line 600, you want to be able to run everything above it, then run this, and then you can proceed with the rest of it. you don't have time to get a coffee. Like it's slower than instant, but faster than doing anything. Yes, yeah. So that's part of the reason that with the first lines are always library commands. And the install you only run once, because install is what pulls it from the web onto your machine. And that's part of the reason I tell people not to use install, not to leave it, is that that's also slow, right? Because it's going to re-download everything. You might see, so sometimes if if you with some scoring of the Prism tools that they've developed, it's quite complicated. But he's got R functions that are calling other R functions, like R scripts that are calling other R scripts a lot. If you're doing that, you might require, when you're stealing code from people online, they might be using the word require instead of library. Library forces a library to load every time. Require checks if it's loaded, and if it isn't loaded, it loads it, but it doesn't reload it if it's already loaded. So the work I'm doing with Jill with that IPD meta-analysis, I've got a different R script for each of the 19 data sets. So I have at the top of those require tidyverse. So it's unlikely the tidyverse isn't already loaded, but I'm to, if it's not loaded, move on. Yeah, no, and that's because in Stata, when you download a library, it's there forever. But Stata has hundreds of libraries and R has tens of thousands, right? Like it's just I think I looked recently because I have to update my R, so I have like 170 libraries installed. Just to load I don't want to wait the extra time because most of those I'll never use again. We'll keep, it's easier to download all of them to figure out which ones I need. Yeah, so this tapply function takes a vector and an index for that vector and applies something to it. In this case, concatenate just gave me all the male values and all the female values so I could do that t-test. So yeah, other ones you might see later. lapply will apply a function to every element of a list. sapply will apply it to every element of a data frame. lapply and sapply are very similar, and I kind of struggle sometimes to figure out why one works and other doesn't. Apply is useful if you want to apply a function to either every row or every column of a matrix. So that's t-tests. We'll talk about chi-square tests in two different. We'll talk about chi-square tests and then we'll talk about effect measures, because the command to get odds ratios isn't the same as the one to just do the testing on our tables. So the command, first thing we do with the table command is how we create tables in R. So if you just run a table on sex and hypertension, that gives you a 2x2 table. And then the command is chisq.test. And you just pass it a table and it'll give you the chi-square test. If you want the exact same results as Stata, you have to set correct equals false. R defaults to a continuity correction. Stata doesn't. It has to do with the normal approximation that we use in chi-square testing. It never matters. But if you're trying to figure out why your chi-square test in R is giving you a chi-square statistic that's like off in the second decimal point, it's because of the continuity correction. And if you go into the help file for chi-square.test, it'll explain what the continuity correction is, and it has a reference for it. I've never gone that deep. I don't care that much. It's never, you shouldn't, if you're in a situation where it matters, probably at a pretty bad sample size for chi-square tests anyway. But the default has that Yates correction. So you can see that if I run the chi-square test, all it gives me is the test statistic, the degrees of freedom, and the p-value. Pretty simple stuff. If we look at what's stored in here, we get the test statistic, the p-value, the parameter. There's some other values that you probably won't use in there. Note that you can also pass it. You can pass the function, the two values directly, so I don't have to create the table first. That being said, you almost always do, because before you run a chi-square test, you want to see the 2x2 table. It's going to be in existence before you run the chi-square test. So I don't know if I've ever run it this way. So the problem with chi-square test, it doesn't give you any effect measure, right? It doesn't give you an odds ratio or relative risk or a risk difference, which is fair. It's not obvious which one it should give you. So it doesn't want to give you all 6 or 7 you might want. So it just defaults to none. Fisher's test does give you an odds ratio. Whoever wrote it just thought it would be. So if I run Fisher's test on the same thing, the output looks more like a t-test, right? It gives you the p-value, the confidence interval on the odds ratio and the odds ratio itself. So Fisher's test does give you that point estimate. And if you dig into what are the elements of the Fisher's test, you can see that there's confident and estimate are the odds ratio and confidence interval on that odds ratio. If you want real effect measures, if you want to get deep into like the relative risk difference, you need to go to a different library. So there's a library, there are probably a bunch of libraries to do this. EpiR is the one I've found that's the most useful, but I haven't checked in a couple of years to see if there's like a smoother way to do this. I like EpiR, I like the output it produces. You can see that it gives you the 2x2 table, the same 2x2 table as before. It gives you totals, and then it gives you row percentages and odds. Those are all the numbers that are used in the creation of the effect estimates. And then this is where, it's not always going to be an incident risk ratio. Sometimes it's just going to be a relative risk. Sometimes it might be a hazard ratio. Like it's the name, it's not all just because you're calculating a ratio of 2 probabilities doesn't mean it's an incident risk ratio. It depends on if what you're talking about. That's fine. That's the relative risk. Odds ratio is always ratio. Attributable risk in the exposed group is that risk difference. Now we can pull all of these out. We can see it actually gives us the Fisher test one. Yeah. This is one of those areas that that Object Explorer I was telling you about can be a little bit of help, because there's so much information that this function produces that it's not necessarily like the t-test produces like 5 numbers. So it's pretty easy to look at all the attributes of the t-test and figure out what you want. With the effect estimates, being effect measures. So one note I should make, what I've done here, loading EpiR in the middle of my script, it's not good practice. You should load all your libraries right at the top. I just, for teaching purposes, it made more sense to put it here. So I created that. I created my table here. Let's pull up this. So we're looking for the relative risks, right? So I see that there's an object called massloc.summary, and then we have the variable, the estimate, the lower, and the upper. Or is that what I pulled it for? Did I pull it from tab? Massloc.detail, my bad. Yeah, so here you can see that it has a whole bunch of things. So the relative risk, the stratified wall for the relative risk, the Taylor, the score, the wall, the C field, and the score for the odds ratio. It actually, if you dig deep into this function, it actually estimates like 17 different effect estimates. They're all essentially the same. Most of them are like if we click through those odds ratio ones, just to pull them out. So, like you can see that the estimate, the odds ratio is obviously the same for all of them. The odds ratio is always going to be the same. What's different is the confidence interval. But even the confidence intervals, the C field one doesn't have a confidence interval. The other ones, they're the same on the first 2 digits. It's the 3rd decimal place that they're changing. So they're all kind of the same. But it has all the different estimates you want. You just need to dig into the objects to figure out which one you need. So the one I pulled out was on if we pull out the Massock summary table, that's the summary table that prints at the bottom. And the first 3 rows of that are probably what you want, the incident rate ratio, the odds ratio, and the risk difference. But if for some reason you need some of those really specialized risk differences or effect estimates, you can get them. And if you dig into the help file on EPI 2x2 and EPIR in general, they have a lot of really complex ways to feed that in. I do find the functions a lot for what is, I really want 3 numbers, right? I want either relative risk or odds ratio. Like, I don't know which one I want. I probably only want one for my summary table. And I want to calculate it on like 12 different summary tables, right? So I want 12 odds ratios and confidence intervals, but I don't necessarily want creating 180 numbers when I want 3 feels like overkill, but it does it right. So I'm fine with it. One contingent specifically, right? You see that I fed in a table. If we look at tab 01, I fed in a table that's got males as the first row, females as the second row, then normotensive and hypotensive as the hypertensive as the columns. And it presented them as the positive exposed and negative exposed group, the positive outcome and negative outcome. I'll defend the function that, like, of all the ways you can arrange this table, this is probably the one that makes the most sense. Exposed as the first row, outcome, positive outcome as the first column. But you need to make sure that R, when you built your table, arranged it in the same way. And R will, because of the way it works, R will organize the table sorted alphabetically. If they're characters, if they're factors, it'll sort them by the factors. But that means that it tends to go low to high, which means that more often than not, it will go negative, positive, negative, positive, which, again, it makes as much sense as anything else. But just you need to make sure that your 2x2 tables are sorted, exposed, and outcome as the first row, first column. If you need to change them, you can just do it with that square bracket subsetting that we talked about in the last lecture, where going 2 to 1 gives me the second column and the first column. That just flips it, and then it's organized in the right way. So my rows actually don't matter because there's male and female aren't exposed. As long as you know, keep track of what the one you fed in was, you can get your effect measure. But I really probably do want hypertensive as my first column. So hypertensive is a state. Normotensive is just normal. So we don't want to be predicting the odds of being normal. We want to predict the odds of being hypertensive. So we need to make sure we're getting our columns correct. It's really difficult thing to in my stats class for the NDI students. I get them to read a paper each week where we like review the statistical methods of that week in the paper. And the 6th time I taught a paper, a student recognized that they'd calculated their odds ratio wrong because they'd had the columns transposed when they calculated it. Like, he was trying to learn how odds ratios work. He was 2x2 table trying to reproduce it. I can't get this to work. Like, and he actually figures, like, I think they emailed the editor. I don't think it ever got fixed because it didn't, like they were reporting an odds ratio of 1.21 and it should have been 1.16. Like, they were within each other's confidence intervals. They both, in fact, significance will always maintain. So, like, no conclusions were being drawn. It was just wrong. As you can imagine, a paper whose primary analysis is a chi-square test on a 2x2 table is not like super impactful. That's a challenge about trying to do. I like doing it, but doing a paper a week in the biostats class, like, well, even 7 weeks in, you haven't really learned any biostats that would make it into most journal articles. Like, it's not till you get into regression that you can start studying the Yeah, right. Like finding the papers that went real deep on box plots was not an easy. Yeah. Yeah, yeah. Like biostats too, you can have a lot of fun with it because you've learned you're learning the methods that get into every paper, right? Where, yeah, especially the first half of biostats 1, until you start learning regression, it's hard to find papers that aren't using regressions and are using analytics in an interesting way. So they're often like kind of toy examples. That's fine. So linear regressions. We'll focus mostly on linear regressions, the LM function. GLM, general linear models, is how we fit our other regressions. And I've talked to Sonia about this, and we've talked about whether we should teach linear regression or whether we should teach everything as general linear models, because that kind of relates linear to logistic more. But linear regression it's so embedded in kind of the culture of how we learn statistics. It visualizes so well that we just keep doing it. You might see some people using GLM instead of LM. They kind of produce the same thing. No, they definitely produce the same thing. The objects they produce are different, right? The object produced by a GLM function is different than the LM function, but not a ton. They all have the same stuff, just called different things. Yes. Yeah. Yeah. So that's the biggest difference you'll find when working with linear regressions is like when you run a linear regression in R, and regressions are really bad for not bad. When you run a linear regression in R, that's it. Nothing happens, right? Something happened, but nothing happens in the output. You just create an LM object. And then so one of the things about linear regressions is like unlike the t-test where when I print it to, when I print it to output, it gives me everything I need to know about the t-test. Here, it doesn't even give me much I want to know, right? Like it gave me the function call, so what exactly I built. And then this is my regression model. This is my x naught, that's x1. Sorry, beta naught, beta 1. And that's it. So you need to go digging for it, but it has all the stuff in there. And it's nice to be able to pull things out. So first thing we learn is the summary one. Right? So the summary on a linear regression model gives you the model fit. It gives you some summary of the residuals. All the residuals are in here. All the residuals are part of the object, but it gives you those summary statistics of it. You can pull out the residuals themselves if you want. It gives you the coefficients. And then down here, we see the model fit statistics. So we can see that here's the adjusted R squared, regular R squared. The F statistic, this is the fit on the full model, whether the full model is significant or not. That's one of the most useless tests we have. It already has them in there, yeah. So if you look at the names of that object, mod.lmo1, names mod.lmo1, mod.lmo1 residuals. So there's all the residuals. It's just a vector of residuals. And then the fitted values. Yeah. So names of mod.lmo1 named component of the object. It's the equivalent of if you were to use the environment browser. And I've really enjoyed this since I've started using it. Yeah, I always thought it was silly until I had to teach myself how GEEs worked here. Or no, there was a machine learning method. ElasticNet is it's like a controlled stepwise regression. If you've ever, you might start seeing papers mention things like ridge regression or lasso regression. They're basically ways to do, because I'm sure you were taught like what stepwise regression is, and then you shouldn't do it. there are ways to do that in a non-biased way. And Elastic Net is the cutting edge for it. It's just the best way to do it right now. But the object it produced was like nothing I'd seen before. Like it doesn't produce an LM object. So I needed like, where are my coefficients? Like I need to pull these things out. Where are they? And I found this browser really useful. So what you see when you do names is these 12 names. So the coefficients, the residuals, I don't know what the effects are. Rank doesn't matter. Fitted values. A lot of these aren't that interesting. Like a lot of these are things like terms and call. Some of the stuff that's saved in here is very much like back end. Things about these is that the summary of the regression model is in itself an object. So if LM produces an LM object, summarizing it gives you that summary. But if we look at the object, it has its own components. Yeah, name it whatever you want. And I would actually recommend, I should go back through this. I've kind of have a little bit of bad hygiene in this report, and I'm calling everything O1 and O2, where like my t-test O1, I should have called it like t-test.sysbp.sex. Like I should have chosen descriptive names. I was trying to keep things as tight as possible, just to, yeah. But I also, maybe just because I'm old, I have a habit of using short variable names, and you can get long with that. You do have to retype everything you type. So, 20 characters is maybe too much, but yeah, so you can any regression models you want, just keep assigning them. Stata has that functionality. Is it eSave or something? Yeah, but it's kind of clumsy. Like you can save it, and then you run a new model, it creates a new one. But if you want to go back to the old one, you have to like activate it, bring it in. Yeah, eStar, yeah. It is, I mean, I do love that family of functions to compare regression models. It's pretty. It's a nice. Yes, yeah. Yeah, yeah. So we'll talk about that as well. This is where the capital AA Nova command comes in. That's the most useful kind of model comparison function you'll see in our where am I? Here. Oh yeah, so I was talking about the summary object. So when you create a summary of the regression model, that itself is a different kind of object. It has its own components. Why that's important is only because what I want is the coefficient table, right? The coefficient table is almost always the most important thing, right? When you're working in Stata, you get the thing you want is that big table of coefficients with like estimate, test statistic, all those. All those parts. Whatever. The coefficient table is in the coefficients attribute of the summary object. So it's a little bit nested, but you don't have to create the object. If you look at what I did here, you can either, yeah, so I can create it and pull the coefficients object out of it. And then that gives me the 4-column X row table that gives me the coefficient for each of my predictors. Then the final thing I wanted to show you was checking assumptions, which I'm sure, as I said there, I'm sure everyone is very rigorous about and doesn't forget to do all the time. If we plot a regression model, it gives us our assumption. It gives us our assumption checking plots. There are 4 of them. It's so slow. The other frustrating thing about assumption checking is you put all that effort in and it gets like half a sentence in the final result. Yeah. No, so the only thing it really affects is the error estimates on the effect estimates. The beta coefficients are right even if assumptions are violated. It's the error estimates that could be wrong. Yeah, like it's the idea that you should be checking each plot for each linear regression model you run. It makes you not want to do linear regression. Because it's like, how can I do this because logistic regression just has far fewer assumptions. It's not nearly as arduous. Makes you think like, can I do this as a logistic regression? There we go. I don't know what went wrong the first time. I messed up my plotting space too much. So here are the four plots. I also gave you a regression that has a violation of assumptions. So that's, and it's not surprising we do. So residuals versus fitted values, normal QQ plot. I don't like these last two, scale, location, and leverage. They're kind of outlier detection plots, and I really don't like outlier detection because it leads to people deleting outliers for poor reasons. Like you should only remove outliers if you have a good reason to. Not if you change this slightly. So if you instead just say which equals 1, 2, that just says just do the first two plots. I don't care about the leverage plots. I want QQ plot for the normality of the residuals, and I want the way outside the normal. Yeah, but honestly, the part of the reason I don't like them is that you shouldn't be getting to the, like, if you have outliers, you should have detected it before now. And if you were happy with your points through your initial summary, like through table 1 and table 2, like you've got all that stuff ready, and then you're finding it's an outlier in your linear regression, it's not really an outlier. Like it must be a valid data point for you to have made it this far. You should have found it in the histograms and the right. Like if someone's got a diastolic listed of 7, it shouldn't be showing up here. Yeah. So yeah, so I say that, and this data set has some cholesterol levels that probably aren't real, and I've been using it for 10 years. I never do anything about them because it doesn't matter that much. Yeah. Yeah, right. Like I don't like removing outliers because of their undue influence on a regression, right? If they're outliers, it's because you don't like their values. So like one of the data sets I have has an age of 160. That's not good. We should do something about that. Either drop that value or set it to 60 or figure out what happened there. But yeah, so they're the normal plots. Do with them what you want. Some of the other commands that are useful here. I'm trying to know what I did to my. Um, oh, yeah, so that's simple linear regression with a single predictor. You're going to be doing most of your work on multiple regression. So now I'm predicting systolic with diastolic, age, sex, BMI groups, diabetes, curse, smoke. Don't worry about too much about the validity of the model. Honestly, like once you factor out diastolic blood pressure, there's not a lot of variance left. So my predictors aren't going to be great. But it's a multiple regression model. So now we get to the point where we might want to evaluate not just coefficients, but also variables. So the two functions we're going to use here. I guess only one of them for the multiple. The ANOVA command. So this is the one that I warned you about, is that you want the capital A ANOVA from the car library. The lowercase ANOVA, I'll show you what it looks like. Sequentially. So yeah. It's called fast, I think, him with the terminology, but type 1 versus type 3 sum of squares. It should be the same for Not even the same for diastolic? What? No, it should be the same for curse smoke. The last one should be the same. Yeah. So the way we evaluate variables in a regression model is build the model with it, build the model without it, compare the difference, and the difference is how much that variable contributed to the model. That's what CAR ANOVA does, right? So this, when we added sex to the model, it removed an additional 14,000 from the sum of squares. What ANOVA does is it adds them sequentially. So it builds a model with nothing, adds diastolic, this many sum of squares are removed compared to the null. Then age and diastolic versus age. Then age and diastolic and sex versus age and diastolic. So like it adds them sequentially. It's called type 1 sum of squares. I don't know why anyone would do that. It obviously must have been you can imagine why it would matter, but in general, I don't want the order I put my variables in the model to influence how important. So type 3 makes way more sense. The problem is that this is how they coded it 30 years ago, and they don't want to change it because it would break people's code, like it would break people's expectations. And I understand that, but you'll see that I tend to always library reference this command, and that just forces me to not use the wrong one by typing a lowercase instead of an it. Because there's nothing, they have the same, like the sum of squares, the F and the P column, actually all of them, this one doesn't include the mean square, but they all have the same variable names. So if I accidentally ran this one and then reference things by variable names, nothing would look out of place, right? There would be no hint that I'd made a mistake. So because of that, I force myself to do the library reference. I think this is the only function I do that. Like I said, there's a variable collision with, I think, the command select with a library called mass, MAS, the letter. So that's the other place where I do library reference. Yes, yeah. So when I don't know if car doesn't have any collisions. I loaded HMIS already, right? Yep. So if I load psych. Yeah. So what they say, the following object is masked from car logit. So if I run logit, it will run the logit command from psych or the describe command from psych instead of the HMS describe. Yeah. Or these two commands from ggplot are replaced with the ones from psych. Yeah, it's very rare for you to not notice function collision because it's so unlikely that the function from psych does the exact same thing as the function from HMIS. So like if I call it on the wrong thing, I get output that looks so much the same, then it almost always just causes an error. The error could be really unclear. So Dippler, like some of the data manipulation we've talked about, has errors that they've worked really hard to try and communicate to you what's actually happening. But if the error you're getting is because the select statement you've chosen is from the mass library, that's all out the window because you're in a completely different kind of area. So you get in trouble with that sometimes. And then we go down to the final thing is getting confidence intervals on your regression coefficients. Now you could do it yourself, right? So if we make coef summary mod.lmo2 $coefficients. If I do that, what I get out is my coefficient table, right? So, and then if I look at coefficient $estimate, this, oh, it's a matrix. You can't $reference the columns and matrices. So if I just take that first column, that's my estimates. So I could do like coef1 minus 1.96 times coef2. Was it 2? Yep. That would give him a lower confidence. So you could do the math to get the confidence intervals yourself. And I've done that a bunch. But there's also a function to do it. So if you just run confident on a regression model, it gives you the confidence intervals on all of your values. Now it doesn't give you, it just gives you the confidence interval. So if you wanted to, I think no, it's just printed out. So I would need to save that to an object. So what I would do is, so these are my coefficients, right? So what I probably want to do, there I go. Confident. Yeah. So what I probably want to do is coefficients. Conf dot two. So I've used a command here called cbind, called column bind, and it binds things together by columns as long as they match the same size. So if you've got a matrix and you want to add a column in front of it, you can column that object in the matrix or add as well. So what I'm doing is I'm binding the coefficients from the model, confidence interval model. And what we end up with there is an object called CIs. And we'll talk next class about how to like get this into a format. Like we could write it to Excel, or we could what cable installed? Yeah. Oh, like VIFs, variation factors, and so yeah, linearity between predictors. From a statistical perspective, that's something I think you usually figure out earlier on during comparisons. That being said, if you want to get variance inflation factors, did you learn about those? Yeah, I can't remember exactly how it's like. Yeah, so they're allowed to be linearly related with the outcome. They shouldn't be too linearly related with each other. So they're non-linearly related. Yeah. It can still be a problem, though, if they're non-linearly related, it really has to be a strong relationship to the point where you should probably be able to explain it functionally. So there are things I would suggest. Oops. So VIF is a command to give you the variance inflation factor. So that's a good one to say, like, is there a problem? The other thing you can do is if you look at the object, saved the data set. QR. So if we make a data set that is just the variables we want. Oh, I'm in the wrong place. That's why I can't find it. Here. So that's just that data set. If we plot that data set, this will produce something. Yeah, there we go. So there are other functions. There's a ggplot function for this that I can't quite remember the name of right now, but this plots all the variables against each other. So it obviously, because a lot of my variables were categorical, it didn't work out great, but we can at least see it. So the first row and the first column are against systolic blood pressure. Those aren't that important. But the next ones, like the diastolic to age, are useful. And then these, there is another function, I'll look it up. There's a ggplot function that will do the same thing, but it'll give you better kind of bar plots for the categorical variables. Multicollinear between categorical variables is really hard to achieve. It only happens when you've got structural relationships, like something that you didn't know this variable causes this variable. Yeah, so if you plot your column, those break down, but there are solutions to kind of help with that. And then VIFs as well is a really easy one to run after the model. I don't love variance inflation factors as a way to evaluate a model. A quick way to, yeah. So the problem with variance inflation factors, they don't do a good job of ruling out multicollinearity. They will detect it if it's there, but they'll also miss it sometimes. So like high VIFs are, you can be confident of multicollinearity, but just because they're all, like, so here we don't, just because they're all low doesn't mean we don't have a problem. You can find it with a specific analytic method. No, they won't, because if they violated assumptions, it's because of problems with the data. They'll correct the data, but then they'll just write up the new data set, right? So they unless it's like an RCT that had a pre-specified published kind of analytic plan, you might, but even then they'll say like, we dropped this variable from the data set due to multicollinearity issues with this, right? Like it's, and the multicollinearity needs to be so strong that what you're saying is like, I don't need both these variables because this one kind of says all the things that this one says. So I'm just going to drop this one. So that's why you don't tend to see it in the published literature. It's that if it was done before we got to the process of writing the analytic output. So the final thing is post hoc comparisons, like always confidence intervals. So let's, in this example, I predicted systolic blood pressure with BMI categories, and then I want to compare the blood pressure between all groups. This is the only place that you use the, when you're learning like stat 1060, we learn ANOVA methods and then regression methods. And then you learn at the end of regression later on that ANOVA is just a type of regression. You ask yourself, why did I learn all those stupid math equations in ANOVAs? So we don't tend to do that. The only reason we need those old original ANOVA methods here is because the functions that give us post hoc comparisons in R expect them. So when we take our linear regression model, this is called casting, where we just take an object and convert it into an object of a different type. It doesn't always work. Coercion is what we see when we convert characters to numbers. But when we cast our regression model to an AOV object, we can run Tukey's honest significant difference. I can't remember what HSD stands for. But it's a post hoc comparison. The other option if you want to work, if you either want to work with your original, with the regression model without casting, or if you want to do post hoc comparisons that aren't just Tukey, like Bonferroni or any of the other 800 ones that exist, Wilcox, can't remember what the, if you load this multcomp library, there's a GLHT function you run in your regression model. And I don't know what LINFCT stands for, but you can see that we can get multiple comparisons. So this library actually goes quite deep. You're not often going to do multiple comparisons, but if you need to, this is the library to do it with. And it produces output that's pretty satisfying. Comp. It gives you the difference between each of them, tells you which ones are significant, etc. So I think I'll stop there. We won't do just regressions. What I'll do instead is we'll work on these first three breakouts. So our glucose levels from between smokers and non-smokers. Is the difference still present after controlling for sex? Is there an interaction between smoking and sex? So glucose is our outcome here, and then we're looking at the relationship between glucose and smoking, and then how sex might be an effect model. Did I say that right? Yes, we're looking at the effect of the glucose levels between smokers and non-smokers and how sex might be an effect modifier. You convert it to a factor variable? So that's, so like for that first one, if you want to do a t-test, it doesn't need to be a factor variable. It just needs to have exactly 2 levels. What did you get? Fine, let me try running. Where does it give you? Oh, I wonder if glucose isn't continued.
It is, yeah.
Okay, so I see what you did. So you created an object called glucose. Oh, is this touchscreen? Sorry. You created an object called glucose that is a new version of this variable, but you didn't change the one that's in the data set. So if you want to change the first one, you would need to add a Framingham first $sign in front of that. Or if you take a $sign referencing off of. Yeah, so that should be.
On its own, we need a $sign.
Yeah, so what you did is you just created a new object called glucose. And so then you're passing that to the function.
So the $sign listed an object, or is that?
The $sign's only the $sign is when you're accessing a variable that's in a data frame.
Okay.
So you could have created this glucose variable in the data frame. That would have worked.
In which case I would have to put like.
Framingham first $sign there and in the function. Yeah. You've just got them backwards. You've got x tilde y and you want y tilde x. It's fine. It's it's one of the confusing things about like you'll get used to the formula operator eventually, but I can really see why people might think of it as x tilde y, because like we read right to left and we're thinking x causes y, that it might make sense that way. So I think the way you guys went was glucose tilde per smoke. That. Yep. So you'll see, for me, rather than do the $sign, I just do the data argument. You can do it either way. It's like I said, for the t-test, doesn't even save typing. It just, I've found, especially since I switched to more tidyverse stuff, I find $signs really ugly. And I find they make code a lot less readable. The other thing we could do here, and I think this is how I was thinking of it, is we could just do a simple linear regression. It'll give us the same result. Yeah, so the reason I would do it as a linear regression is only because this lets me cheat and do half of the second question with the first question. How do you adjust it? I actually just can't. So if we want to, we only got 2 minutes left, so we'll do these last ones. So what I say, sex? So we just add sex with a plus operator. And it looks the same. We can do the summary objects. And then for interactions, I didn't show this to you, but interactions are just done with a star. Yeah. And then we get the interactions insignificant, so we should just throw that model away. Oh, I should make that yes, we'll stop there because it's 12:30. This is something you guys to really work hard. Functional reporting. So we'll start with functional reporting, and then we'll dive back into like the rest of analysis. But one of the if you can get your data set clean at the beginning and you're happy with it, it makes everything else easier.
I find that sessions are good as well.
Right? And like the data cleaning is so fresh, but it's part of, again, functional reporting, we'll talk also about like code organization, things like that, is that comes in so many steps, right? Like you're iterating through your data, you're getting everything tidied, and then you go start your table one, you're like, oh man, this date variable's broken. If you're disciplined about how you organize your code, you can go back up, fix the date, rerun everything, and it only has to happen once. But it takes that discipline, because the problem isn't the analytics, right? The problem when you guys are getting errors, it's almost always because of a data quality issue, like a data manipulation issue, and that takes a lot of practice. Oh, are you in are you having that issue where it's displaying in your R&D file and not in your? Oh, you're not in. So it's in an R&D file. You're not in a no web tag. So again, we'll start with this next class, but I'll show you on here is that when you're in RMD files, they have R sections and text sections, and you're in a text section right now. So you can see that here, like my code is between, that's a bad example, that one's too big. Here, all my code is between these, we go tilde, 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 open brace, R. You don't need this one, this is just the name of the chunk. Close brace, and then tilde, tilde, tilde closes it. So everything between there, it knows is our code, and you can see it colors it slightly differently. The stuff outside it is text. So you need to embed it within a code chunk, because otherwise the editor doesn't know you're trying to execute things. Tuesday, yeah. We go Tuesday and Friday next week as well.